Now, why did this happen? Why did this happen? This is the Big Bang, if you will. The Big Bang of computer perception. The Big Bang of computer perception. And why did it happen now? Well, three things. Of course, the invention of this, if you will, general, unprogrammed, and I will go way too far and say simple approach, and Jan would always say this is the simple design of a network, inspired by biology, something that you can train with an enormous amount of data and a massive amount of computational horsepower. This design made it possible for us to use this network on so many things and for so many people to be involved, because we don't each have to design our little features, if you will, our little hog feature detectors, histogram of gradients, or SIF detectors, and so on and so forth. We can now use this basic design and architecture of a network and use it literally to train on almost any data. The second thing, of course, is the emergence of large data. It would have been possible without the internet. The researchers at Stanford, under Fei-Fei Li, worked on this database, the world's first hierarchical database, and it has 15 million images in it with 22,000 categories. And it's all hierarchical, meaning that underneath dogs, there's a whole bunch of species of dogs, and underneath fruit, there's a whole bunch of species of fruit, and underneath, above dogs, probably mammals. It's completely hierarchical, and it's all labeled. There's still some error, of course, in it, but it's largely labeled correctly, and it was largely labeled correctly because of one thing, the emergence of Amazon's Mechanical Turk. I don't know how many people contributed to this work, but obviously a lot, and they all were paid. Fei-Fei tells me that it's 4 cents or so for every image that they somehow tagged. And you could imagine, without the internet, without big data, without all of those cameras, all taking pictures, and these pictures are kind of messy. Lighting conditions not always right, the orientation's not always right, there's a whole bunch of different versions of the same thing. Somehow, these 22 million images tagged by humanity off their cameras all contributed to this hierarchical database called ImageNet. Because there's this one standard large database, we now have access to data. All we need now is a supercomputer. And that's our contribution. With the invention of CUDA, with the invention of GPGPU, and putting it into the hands of literally every researcher in the world, Titan became the platform of choice of deep learning network researchers all around the world. Those three things together, the democratization of supercomputing, if you will, large data, and the invention and the observation of one brilliant scientist in 1995, and then all the contribution of work since then, resulted in the Big Bang, 2012, the Big Bang of computer perception. Let's take a look at this network, shall we? This network is interesting. Inspired by the human brain. It doesn't work like the human brain, it's inspired by it. Whole bunch of neurons. The neurons are modeled as little tiny simple processors. There are 3,000 processors in the Titan X, running, call it, at a gigahertz, at 1 billion cycles per second. These processors are connected with each other, of course, on one large internal fabric, using this idea called shared memory that many of you know about. This network composes of a whole bunch of neurons, little tiny processors, and these neurons are connected to other processors. The connection it has with other processors are weighted, depending on the importance of that connection. There are receptors on the top layer, or excuse me, the bottom layer, as it turns out, which is on your left. Oh, you know what? I thought I was talking to that slide. Mike, could I go back to it real quick?
Sure.
Okay, there you go. Sorry. Thank you. Now, one of the best things about GTC's keynote is we don't rehearse very much. And people always say, hey, Jensen, it always seems so spontaneous. Guess what, guys? Here's the way I think about it. We should be preparing all year, huh? And so this is just game day, okay? We were preparing all year. And so let's think about this network. On the left-hand side, these are essentially, right on the other side of it, are basically receptors of your retina. And these things are connected to neurons that apparently detect certain orientations, otherwise known gradients, of these edges. Somehow, over the years, these biological things, we recognize edges, a whole bunch of them. And we recognize textures, combination of edges. And so what's amazing about this thing is this network starts out with these receptors. In this case, this particular network is AlexNet, has 5 convolution layers, which is represented by the green boxes. And each one of those boxes increases the scale of recognition, if you will. The lowest level, the flattest level, is looking at small features across the entire image. The next level of scale, it might be looking for what I mentioned earlier, textons or patches of textures across a higher scale or a lower resolution of the image. And then after that, it could move up another scale, look for parts, and then so on and so forth. The last few layers, those patches of colors at the end, are what they call fully connected layers, and it assembles these parts, if you will, into a vector, recognizing it as a car, if you present it with a Ferrari 458. And so this network, the convolution neural net, was the invention of Jan LeCun in 1995. Obviously has evolved greatly over the years, but a lot of the basic ideas has retained. Now, Mike is going to give us now, this is Mike Houston, he's going to give us a visualization tutorial of how this network works. Now, what's important to understand is the amount of computation that's within it. Each one of these volumes, if you will, is doing convolutions simultaneously across all of those weights, across all of that image. The simultaneous computation of layers and layers and layers and layers of convolution, which is a mathematic term for testing for a particular patch of filter across an image. Okay? Mike, take it away.
So as Jensen said, what you're seeing here is a finally trained version of AlexNet. So the green pieces, again, are the filter banks, these convolution layers that we've built. The red images that you're seeing are actually the activations. And then the images to your far right are the fully connected layers. So let's rotate the network, and let's fly through it mathematically, how this image is being applied through the network to get its final result. So we're going to take our cute little bunny here, and we're going to walk through the network. So we're going to take this bunny image. We're going to apply all these linear filters. These are these edge detection filters that Jensen was describing. They're also known as Gabor filters, and they represent sort of the visual cortex in the human brain. They're a good analog for that. So we multiply each of these filters across the image to get the resulting activations. So there are 96 filters, and so we get 96 activation outputs. And then we take that, and we go through an extra step that's unique to AlexNet. And what this step actually does is it amplifies and selects the dominant features that are then fed in to the following network. We're going to continue to apply all the way through these weight networks as we fly through the network until we get to a fully connected layer. So each of these is increasing its abstraction, sort of how deep the feature descriptor is and what its parts look like. And then the first fully connected layer is going to take those parts and begin to mix them together. So if we continue to fly through, and we're going to shift so you can see the output vector here. In this case, this is the output result, this histogram, that high-dimensional vector, the 1,000-dimensional vector. So if we take our bunny, this is the output of bunny. So you can see that really strong bar. So it turns out that the classes here of bunnies are grouped together. It's actually an angora, but the network actually understands even subspecies of rabbits. So we can actually look at how that changes as we change other images. So for example, we put a dog through. As Jensen said, there's lots of species of dogs, so we get a lot of activations, but we get a few in particular. So this is actually a mixed breed, which is why it has a couple of very white, bright bars in it.
What is this dog, by the way?
Does anybody know what that dog was? So it's some type of hound mix We actually...
Ask Andre, he knows.
Andre, do you actually know what dog that is?
Go. Okay.
So, and here's a koala. So the koala is an interesting one because the network actually struggles here. It gets koala as the highest output, but if you look at all the other ones, you get things like squirrel and other types of sort of small mammals. And similarly with a cat, you kind of get a similar sense where it's still grouped sort of in mammals, which is why you still get that sort of histogram chunk there. But again, there's multiple subspecies of cats. So that's taking a fully trained network and going through and seeing how it outputs things. So let's switch and look at actually training a network from scratch.
Now, Mike, before you start, remember, this is how the network starts. It's a bunch of random numbers in it, and it's largely unprogrammed. I mean, all that's been done here is that the architecture, which requires some amount of understanding about imaging and such, the architecture of the network was designed by the engineers. The architecture of it was designed. How many layers of the convolution? How many layers of convolution networks before you apply them to the fully connected layers? How wide and how deep are these convolution networks? All of those parameters were somehow engineered somehow by the data scientists, but it starts out not able to recognize anything. Okay, go ahead, Mike.
So we're going to start from a blank slate, as Jensen said, and then what we're going to do is we're going to start pumping lots and lots of images through. We'll push those through the network. It'll get a result. The result will be wrong. It'll modify that result and then back propagate and basically correct all the error through as we go. So if we watch us put in images, what's amazing is how fast those features in the front actually form. Those edge filters form almost instantly, and they maintain fairly stable. So this is an interesting property of these networks. The remaining training actually happens in the much later layers. What's happening as the accuracy increases, the learning rate is decreasing, so the rate of change is also decreasing. So we actually reach the point where the human eye actually can no longer see changes because they're so minute in the network. So as this network goes through, it basically gets smarter and smarter, and then researchers basically keep training until it begins to stabilize all the way out. So if we look at a comparison,
by the way, all of this is being visualized. This volumetric rendering, visualization, is in itself very complex. This is being visualized on a volumetric renderer we call Index. Index gives you the ability to visualize very, very large scale volumes, such as seismic processing or imaging, medical imaging or such. And we're using it in this particular case to visualize the enormous volume of a neural network.
So this was AlexNet. So for comparison, remember this was just a few years ago. For comparison, let's look at actually one of the winners from last year's. So if we look at the VGG network in comparison, it's a tremendously deep network by comparison. So you can see how big it is. It's a 19-layer deep network. So this improved the accuracy tremendously and shows a big shift. If you remember how big the volumes were in AlexNet, you notice how small these are. They've switched to deeper, sort of narrower volumes. It's actually a very interesting result in modern neural networks. And this is now the basis for most of the current continuing research. Most people use this VGG network, and the accuracy is a significant jump over AlexNet. You can get the sheer scale of how big these things are now getting.
That's great. Thanks a lot, Mike. So Mike just wanted to give you a flair, a sense of what a deep neural net is about. One of the things he mentioned earlier that's really important to realize is that when we trained this network, we showed it an image, and we compared it on the other side at the output of it. Initially, when the network is completely empty, we compared it to what is the right answer. And if it's wrong, we compute some kind of an error function, and we back propagate that through the network, adjusting all of the weights along the way. Okay? And it would do this over and over and over and over again, and that's one of the reasons why it's so computationally intensive. Lots of mathematics involved in the neural net itself, and you got to do it iterations after iterations after iterations. Now this particular, the Big Bang in 2012 caught so much attention around the world. Anybody who's a data scientist, anybody who's working with unstructured data, anybody who's looking with big data, anybody who's trying to predict the future, predict what's about to happen based on patterns, uncomputationally extracted patterns, impossible to compute patterns that are observed in a large amount of data. People who are doing that, who have those kind of needs, are jumping into deep learning. The number of companies that are involved in deep learning has just exploded. Now, this is a partial list. But the important thing is this. The partial list includes everybody.